Good afternoon, dear audience. Thank you for the invitation. I'm Igor Fedin with the University of Alabama, and today I'd like to tell you a story of using 2.5 semiconductor quantum dots as shortwave infrared emitters. What is shortwave infrared? Well, it's a spectral range from about 1500 to 1700 nanometers. It falls between the overtone of the OH vibration and the overtones of NH and CH. Uh, for that reason, media such as silica, atmosphere, biological samples are the most transparent to this spectral range. Therefore, this radiation is used for telecommunications, self-driving vehicles, defense applications, and biological tissue imaging. Thanks to the lowest propagation losses, absence of chromatic dispersion, and that's the range where lanthanide doped amplifiers operate. Therefore, we need shortwave infrared emitters. We know many organic chromophores that are particularly bright in the visible region, reaching 100% quantum yield. But when we look at quantum yields of organic emitters, the infrared, they decay exponentially as we move to the infrared region. And there is a reason for that. What happens is that the electronic energy is dumped into the vibrational modes of the molecule. Therefore, to serve as an infrared emitter, our molecule or structure has to be rigid, cannot be floppy. So we need solid state emitters. For example, semiconductor emitters. Uh, to be an infrared emitter, short-wave infrared emitter, semiconductor needs to have a narrow gap. And naturally, that happens toward the bottom of the periodic table. Germanium itself is a narrow gap material, but it's an indirect gap semiconductor, so it cannot serve as an emitter. But for example, 3.5 semiconductors, indium gallium arsenide, lead chalcogenides, mercury chalcogenides, are examples of narrow gap materials that can serve as short-wave infrared emitters. Semiconductor carbon nanotubes can serve as infrared emitters as well, but they are rather toxic. We would like to avoid them. In the epitaxial world, most abundant short-wave emitters are indium gallium arsenide with tunable emission wavelength. Our community would like to bring it to the colloidal world, and the groups working in that direction, including the group of Munjiba Wendy, Nobel laureate in quantum dot chemistry. And his group showed emission from indium arsenide quantum dots reaching past 1500 nanometers, but naturally we see that the quantum yield decreases as the emission reaches shortwave infrared. Similarly, 4-6 semiconductors, lead sulfide, lead cyanide have been explored extensively by a number of groups at NREL and other groups. And quantum yields were collected for a number of samples, and again we see the decline in the quantum yield is with the increasing wavelength of emission. Mercury chalcogenides have been picked up in the recent years. Well, they were pursued intensively by Philippe Giossione. Here we show emission by mercury selenide between 1800 and 2000 nanometers. Other groups have also worked in this direction, including Andrew Smith. And mercury telluride has been picked up in the recent years, for example, by Justin Karam at UCLA, who showed emission quantum yields up to 80% for 1100 nanometer emitting dots. In my group, we're developing cadmium phosphide as an alternative short-wave infrared emitter. It's an overlooked material. I like to call it the infrared cadmium selenide. Why? Because as far as the synthesis processing goes, it's a lot like 2,6 semiconductors, cadmium selenide. But it's a narrow gap material, the bulk band gap of 0.575 electron volts. It's a direct gap semiconductor. The effectiveness of the carriers are fairly light, in particular the electron, which suggests a large exton Bohr radius and strong quantum confinement. As we make the quantum dots of cadmium phosphide, the band gap will open up dramatically. The first reproducible synthesis of cadmium phosphide quantum dots was reported in 2010 by two groups in parallel, Shagan Pan and Alexander Eichmuller. So here I'm looking at Eichmuller's synthesis using cadmium carboxylate and trimethylsilyl-phosphine. And exactly what I was saying, if we just use the precursors, we produce quantum dots emitting between 7 and 800 nanometers, which correspond to band gap larger than 1.5 electron volts, despite that narrow band gap in the bulk, with precisely the strong quantum confinement. So to make these quantum dots emit radar, we have to grow them larger. And there are tricks to make that happen. One of them is to nucleate the quantum dots under the conditions of high solubility by using acidic solutions. For example, C injection of lactic acid shifts the emission to the red, well, yields larger quantum dots that emit radar, or using coordinating agents such as triophosphine, for example, here, which coordinates to cadmium and again solubilizes tiny dots of cadmium phosphide, also favors the formation of larger dots which emit radar. 2 years later, the same group produced quantum dots emitting at 1300 nanometers, but they used phosphine gas in the synthesis, which we would like to avoid. We're using trimethylsilyl-phosphine as a phosphorus source and cadmium oleate. And in our first syntheses, we were producing quantum dots emitting, well, in the size range from about 4 to 6 nanometers, emitting from about 1000 to 1200 nanometers. The crystal structure of cadmium phosphide is tetragonal. The unit cell is a square brick. And these quantum dots are very air sensitive. Natural solution is core shell structure. At that time, we were trying to develop the cadmium selenide shell. Unfortunately, injection of top selenide into cadmium selenide dots immediately converted them to cadmium selenide. So we have initial solution cadmium phosphide, which is black, few droplets top selenide, black turns orange. We developed an adhesion layer of cadmium selenide using special treatment, selenium aluminum, and then on top of that adhesion layer, we're able to grow cadmium selenide. Of course, we wanted to push the emission to shortwave infrared, so we looked into how to grow larger dots. We explored a number of parameters. One of them was the injection temperature. What we noticed was the higher the injection temperature, the smaller the dots. Makes sense for our highly reactive trimethylsilyl-phosphine. It's highly reactive, so when we inject at higher temperature, it breaks, forms many nucleation centers, which consume the precursor, and then we end up with many dots that are smaller in size. Now, the factor that really played the role was the acidity. When we increase the concentration of free lactic acid from 0.20 to 0.26 molar, we're able to grow larger dots and shift the emission from 1215 to 1480 nanometers. For some dots, overgrowth works, not for cadmium phosphide though. An injection of cadmium precursor, only cadmium iodide, works to increase the size a little bit and shift the emission, but only for smaller dots and only up to a limit, and doesn't work for larger size. A combination of cadmium iodide and the acidity does help us grow larger dots and shift the emission to 15-30 nanometers. Here, with help of an integrating sphere, we're able to measure quantum yield of 31% at 1250 nanometers. We were able to synthesize quantum dots in the range of sizes and construct the sizing curve, which is handy because it allows to determine the size of the dots without measuring microscopy every time. We also saw that, we had just these black data points at the time, and from the sizing curve we saw that to emit in the short-wave infrared, the quantum dots would need to be larger than 10 nanometers in size, diameter. One way to achieve it is to overgrow clusters, which was previously reported in the literature, including for indium arsenide. There are atomically defined clusters of cadmium phosphide, which were first reported in 2009. We synthesized them. And these clusters show spot-on reproducible absorption at 451 nanometers and spot-on reproducible emission 455 nanometers. In parallel, the group of Brandy Kassar also synthesized these clusters, tried to characterize them. In particular, they were looking at the effect of the surface ligand capping on the photolysis quantum yield and also on the photolysis dynamics in cadmium arsenide clusters. We were trying to determine their molecular composition. For that, we turned to mass spectrometry. We compared the mass spectra of the dots and the clusters here, and the dots show molecular ion band at 40,000 atomic units, corresponding to 100 units of cadmium phosphide. The cluster did not show molecular ion peak or band, but showed the sequence of fragments with decay intensity. We tried to identify those molecular weights of the ions and assign the formula. And the second heaviest fragment here corresponds to composition cadmium 32 phosphorus 20 085. Then slightly lighter fragments corresponds to cadmium 29 phosphorus 18 with 0.1 atomic unit. It suggests that these clusters are at least 10 units of cadmium phosphide with all 8 capping ligands. When we inject the precursors into octadecene at 108 degrees, we see emergence of these clusters and then their decay, and again at the same wavelength, and the growth and redshift of a red spectral band, which corresponds to the growth of quantum dots. Next, we used cadmium phosphide quantum dots as seeds and injected cadmium phosphide clusters there. What happened through osphole-ripening, clusters dissolved and overgrew onto larger dots, similar to what happens in clouds. And for when we use small cadmium phosphide dots as seeds, we observed growth of cadmium phosphide from clusters in them. Larger cadmium phosphides first etched and then overgrew. And then some of them were able to reach decent quantum yields, up to 1400 nanometers emission, but we weren't able to exceed 1400 nanometers. So we had to turn back to our conventional syntheses, optimize the injection temperature, duration of the reaction, the amount of lactic acid, and we're able to produce a sample that emitted past 1530 nanometers, where our detector stopped, and with the near-infrared photomultiplier tube, we're able to see that the emission was close to 1600 nanometers, the emission peak. Dots were about 10.5 nanometer in size. They're quite faceted. Then another sample of cadmium phosphide. Here we use the combination of our indium gallium arsenide detector and photomultiplier tube and show the emission in this sample is about 1540 nanometers. By analogy with 2,6 semiconductors, we produced alloyed cadmium zinc phosphide structures from their interplanar spacing and X-ray diffraction, and given the content of zinc doesn't exceed 28% by metal, we conclude that these dots have a well-defined cadmium phosphide dot and then cadmium zinc phosphide crust around them, which provides the stability and enhances the luminescence. We can work with these dots outside the glove box, while pure cadmium phosphide is sensitive. Time resolved spectroscopy is very informative of the emission channel. Pure, because we see that, for example, cadmium phosphide, cadmium zinc phosphide can have very similar spectral features in absorption and emission spectra, but can be quite different in time resolved luminescence. Pure cadmium phosphide is a slow emitter, and band edge radiative recombination time is characteristic of a semiconductor. For example, cadmium selenide has the emission time of 20 nanoseconds. Here we observe hundreds of nanoseconds, which suggests that emission is not band edge, but the hole gets trapped at surface phosphorus atom. The phenomenon is similar to what was described for 2,6 semiconductor quantum dots. How to mitigate it? Well, one way is to overgrow shells, and we see acceleration of emission, cadmium selenide shell, or alloying zinc. But what really impacts the dynamics is coordination of Lewis acids, or also called Z-type ligands, which coordinate to the surface phosphorus atom and push this lone pair of electrons down below the top of the valence band, and it stops acting as a hole trap. We also turn to transient absorption spectroscopy and observed that the loss of 30% of the excitation state when early in the first 300 of picoseconds, which in combination with time resolved photoluminescence is consistent with 30% quantum yield. Well, this is an example of our reddest emitters. 15 cadmium phosphide emitting 1530, cadmium zinc phosphide emitting 1570. We see that they are quite faceted, cubic prismatic in shape. And here we see particularly slow emission of cadmium phosphide, and then we see that cadmium zinc phosphide depopulates its photoluminescence by more than an order of magnitude in the first emission lifetime, and we were able to get lifetime about 60 nanoseconds for cadmium zinc phosphide, which is likely the band edge radiative recombination time in these quantum dots. We were trying to measure the single dot emission from these dots. We weren't able to because of the strong blinking, but when these likely we were looking at small clusters of them rather than single dots, and we saw dramatically increased emission rates from this small cluster of quantum dots. See emission time of 17 nanoseconds, for example. Finally, to extend this to 5 semiconductors, we moved to mercury phosphide, which has not been synthesized before. It's very interesting. Sometimes we're making chunks like this. Sometimes we're making quantum dots, which show facets. And we're looking at elemental composition in them. Here, for example, mercury shown in these large bulbs, so that's work going on. Finally, I'd like to thank my group and the collaborators at Argonne National Lab, University of Oklahoma, Los Alamos, University of Illinois, and the funding by the NSF. Thank you very much for your attention.